Today we are going to look at classical machine learning algorithms. We have spent about a week, last week, a week and a couple more days. We looked at regression. Regression is essentially the foundation of machine learning of any sort. Regression allows us to understand it from first principles. Regression allows us to tie it back to basic maths so we can even visualize it and understand how it works. Once you go beyond the regression, linear regression, logistic regression, we now go into the area where it becomes more difficult for you to use simple maths to represent it. But what I can tell everyone is that at the end of the day, it is more or less the same principle. We are still using essentially a system of linear equations or system of equations to represent a complex system. And when we say learning, you are still doing the same thing. We are still updating parameters, and those parameters are coefficients of the features or the independent variables, that make up the system of equations. That's really all there is. Of course, it's not as simple as that, but that is, helping us to understand. Beyond regression, beyond linear regression, beyond logistic regression, we now go into a lot of more complex methods that are used in machine learning. Because, of course, linear regression is not enough to solve problems. And we're going to even talk about that when we go into decision boundary and all of that. If you're using a linear equation for a classification task, your decision boundary is going to be a straight line. So for complex systems, for complex, interactions, for complex relationships, it will be very difficult, but it's impossible. So that brings us to these new methods. So we are going to look at using classical machine learning methods. Before we go into that, we are going to take a little dive into scikit-learn or scikit-learn, which is a science kit. Basically, that's what it means. It's a scientific training kit for training machine learning models. And it is built on top of CP or SciPy, which is a scientific library for Python. It is also built on top of NumPy. We're going to look at that. So this library, which sometimes we call it sklearn, allows us to do all of those things that we did last week, where we did a lot of equations and we went through a lot of steps. With sklearn, it becomes very easy. A single line of code, that's all. And you get the same thing. So and that tells you the benefits that these libraries bring, because if you were doing it yourself, you know how much work you would have put in, right? So with sklearn, right, we will do the same classification problem. We'll do the same regression problem, and I'll show you how much easier it is. Then we'll now talk about the additional algorithms, methods for machine learning, for modeling data and training those models. So it's not just linear models. We now have decision trees, and then random forests, which come from decision trees, and then gradient boosting, which is a special form of gradient descent that was customized for decision trees and random forests. Then we'll talk about support vector machines, k-nearest neighbors, and all of that. Then we'll look into clustering and dimensionality reduction. This is a whole lot. We're not going to dive deep into it much, but we'll just go through so that we understand. So let's start with basics. The same classification and regression that we did last week, we will now do with sklearn, scikit-learn. Like I said, scikit-learn is a library that is used for machine learning. What we call classical machine learning that wasn't really around neural networks. Neural networks require a whole different kind of algorithms and computational power. So Yes, sklearn can actually do a bit of neural networks, but they are not as good. It's not as good as the other ones like PyTorch, TensorFlow, JAX, and all the rest. So a lot of people use sklearn for basic stuff in the machine learning area. So like I said, it's built on Python libraries that we've already looked at, such as the NumPy, which we use for numerical operations, SciPy, which is for scientific and technical computing, and it's also built on Matplotlib for data visualization. So it's a comprehensive collection of algorithms. It gives you a vast array of different machine learning algorithms for different tasks. So for example, for classification task, it will give you algorithms like support vector machines, which we will talk about and explain what that means. Decision trees and random forests. We'll talk about that as well. K-nearest neighbors, logistic regression, which, well, that's what we just did last week, but it makes it much easier. And then for regression problems, the linear regression, which we also did last week, but again, it makes it much easier. Then we have ridge regression, we have lasso regression. These are all different approaches. And gradient boosting, which is for the random forest and so on. Then for other types of problems like the clustering problems, which we talked about, the unsupervised learning problems, we'll talk about k-means and dbScan. We'll talk about agglomerative clustering, what those things mean, and how it is so easy to do those things with sklearn. Then dimensionality reduction, we'll also explain that and how we can do that. There are different techniques, but the most common one is the principal component analysis, a PCA. But we also have the linear discriminant analysis, which we'll also look at. Basically, these dimensionality reduction approaches are used for when the information has a lot of features which you cannot visualize. So think of a data set that has maybe 100 features. That's multidimensional. And you want to plot it on a graph. Which one do you plot on the X? Which one do you plot on the Y? Which one do you plot on the Z? You can really only plot three on XYZ axis. You can only plot three features if you want to see how they correlate. But if I had 10 features and I want to plot it on a graph, that's the dimensionality reduction allows me to pick the most important features and even adjust the values of the data into 3 dimensions, which I can then plot and it will still kind of represent how that data is. Yes, some information is lost, but it allows us to still see the data in a 3 dimensional plane, using the standard visualization approaches, which Matplotlib and other visualization libraries will give to us. So that's the benefit of dimensionality reduction. The other thing that sklearn gives to us is what we call a training pipeline. So it allows you to use a single pipeline that you build for training, right? And the training pipeline is not just the model itself, but even the data preprocessing. So it actually starts from the data preprocessing. And then after the data preprocessing, right, it goes on to model selection. It goes on to model evaluation, right? Then it goes on to efficiency and integration, right? So these are some of the things that sklearn will allow you to do. We'll talk about that. But one thing you need to understand is that in the data preprocessing part of it, you can do feature engineering. You can do things like scaling and normalization. We're going to talk more about that when we get into feature engineering. But you'll be able to do scaling, you'll be able to do things like normalization, handling missing values, which I did some examples of that with pandas. So interestingly, scikit-learn also allows you to do that. Then we have model selection, which allows you to actually search through different types of model architectures and train them maybe on a small amount of data, do validation and evaluation, and pick the one that gives you the best, right? The other thing, that's model selection, and it can be automated. So it allows you to do that. Then it also allows you to evaluate models. So you have standard metrics, for example, accuracy, precision, recall, then F1 score, mean squared error. We already talked about mean square error, and you saw how you can calculate. It's not really hard. It's a one-liner with NumPy, but scikit-learn also provides that. But others like precision and recall and accuracy may take a bit more. Again, sklearn allows you to do that. So the other thing it allows you to do as part of data preprocessing and model selection is efficiency, right? And integration, because of course it's built on top of NumPy, which already has been optimized for efficient numerical calculations that are needed for machine learning. Then, of course, there's an open source community to support. One other thing that you really love about sklearn is this consistent API. So the way you write the function call, the way you call the function is the same. Whether you are doing linear regression, whether you're doing logistic regression, whether you are doing data preprocessing, whether you are doing um, decision tree, random forest, whatever algorithm it gives you the same thing. So you don't need to try to remember, oh, for this do I do, or for the other one, how do I do? Once you are able to learn and master one way of doing things, that same approach is what you use for all the other ones. So it makes it really easy to learn and to use. And it also makes it easy for you to switch between different algorithms and approaches without having to rewrite your code. In fact, that's the primary benefit of having that. So we will we will start off by just getting a little idea and understanding of how to use scikit-learn, okay, sklearn, to do basic classification and regression, what we already did. So for that, I'm going to essentially pull out the same data set that we used last time. So remember, we had a data set when we we're talking about vectorization, and we used that data set to um, create, we use it to create, or we use it to do logistic regression. So, but I want to start with that same data set, right? And then I will use it not for, I'll use it for the basic linear regression. Then I'll use it for, of course, that's also multivariable linear regression. Then I'll also use it for logistic regression. So it's really very easy to use. So for you to use sklearn, the first thing you have to do, of course, you import the library. So it's actually very easy. You import the library you want to use. So for example, if you want to use linear regression, you sklearn, right? That's how it's called. Um, Models. Then you import linear regression. So this is how simple it is, right? It's as simple as that. Okay, this should be linear model. So linear model has a different, so that's it. You import that. Then the other thing you could do is for matrix, calculating things like mean square error and so on. You you can also get from matrix. So we can import mean square error. So we will need NumPy as well, as usual. And we will need matplotlib as well. The pyplot, right? As PLT. So these are the four basic libraries that you get. Now I'm going to get the data set that we had um, in the last one that we just did last Monday. So I'm going to get the data set, and then I'm going to use that same data set for our regression. So if you actually look at this, right? So let me show you this because we already have that. So you can see that same data set, okay? Just this X and just this Y. Now, there are some interesting things that I want you to learn as part of sklearn. It's good for you to go to their site and look at their documentation. You can go check it out. Scikit-learn. They have very good, extensive documentation, and you can do a lot of things with it. They have examples here. So, for example, if you want to do a classification problem, you can just go look at the ordinary least squares model, which is what we use. Okay, which is what we are using for this, right? Basic X and Y. So this is the same thing. You take X and Y. So here's the data, and I can easily plot this with matplotlib. Plot.scatter, a scatter plot, basically X and Y. Okay, so that's the scatter plot. Of course, you can see there's still a pattern here. Now, to show you how easy it is with sklearn. After you do this, it is very easy for you to now create a model. So remember before when we were doing our models, we would have said model equals, we would have to get an M, right? If we want to use the normal manual linear regression, C equals this, and then we would have done Y equals MX plus C, M times X plus C, right? Right. The model contains the parameters. Okay. So this is what we were doing, right? Now you could say that using the linear model or linear regression model is probably too complicated. Okay. But this is a start. So with linear regression in sklearn, you simply do this. You create a model. Model equals linear regression. So I have created a linear regression model. Then you fit. You'll find that, remember we said that it's the same API. It's uniform across, right? When you're using sklearn, it is a consistent API. So this consistent, you see that it's always going to be the same pattern where you create a model and then you fit the model on the data. So model.fit. And when you do model.fit, you have to pass in the data. And I need to explain why we need to do this reshape, because if we don't understand this, then we'll have a problem. Let's start off by looking at the actual shape of the data. If you look at this data, you see that the original shape of the data is 20, comma, with nothing. So this is a tuple, which is a data structure in Python that is used to represent, composite numbers, a composition of several numbers. So in this case, what this means is that This particular data set has 20 entries, 20 rows, but the columns are not considered. In other words, it's a single vector, right? So we are not bothered counting columns. Okay, so it is a vector of 20 elements. That's what this means for X. For Y, it is also a vector of 20 elements. Okay, so that's a shape. Now, if I were to take this XY and use it to fit in the linear regression model without reshaping it, I'm going to have an error. And the error that I'm going to have is that the shape does not match for Y. Basically, your data reshape, it says expected a 2D array, got 1D array. It's as simple as that. So this is a 1D array, a one-dimensional array. A vector is a one-dimensional array, right? When you are doing fit in sklearn, the X must always be a two-dimensional array. So a two-dimensional array is a matrix which has rows and columns, okay? So even though this is still one-dimensional, but we have to specify the second dimension. That's what this is. Because sklearn is designed generically to be able to handle matrices. So what you pass into it must be a matrix. So something that has a shape of 20 is a vector, it's one dimensional. And this one is also a vector, it's one dimensional. A matrix is two dimensional. So what reshape does is to convert it into a two-dimensional array. And how does it do that? Model.x.reshape. Now this reshape has a special meaning and syntax. So I'm going to try to explain what it means. So now we are going to print this, right, as it is. You can now see that after reshaping it, it is now 20, 1. That means it has 20 rows and 1 column. But you may ask yourself, was it not also 20 rows and 1 column before? Yes, it was. The only difference is that then it was considered as a vector, right? In a vector, the columns are not recognized. We don't even bother. We don't count it. That's why it was just 20 comma, nothing specified. But now we have converted it that it is effectively a matrix that has 20 rows and 1 column. From the standpoint of you or I is the same thing, right? But for the purposes of understanding and uniformity, right? They are different. So reshape does not actually change the data in a um, you know, in a tensor or vector. It doesn't change the data. If I do reshape now and I print it so you can see the actual data, you see that it's the same. It's the same. In fact, let me do this. Let me print the reshaped X against the original X, right? The main difference, let me now show you the main difference because you can see that there's a difference in how they are printed. The original X is printed in a row-wise format. See, it's just a single list, single row. Okay, the orientation doesn't matter. A vector, the orientation doesn't matter whether it's vertical or horizontal. But here the orientation now matters. So it has to print it vertically, where you now have this, meaning the number of rows, and a single column. So it now has a two-dimensional shape. But here it was a one-dimensional. Okay, so that's what reshape does. You can see that the content is the same. It didn't change, right? It's just the arrangement. Now let's explain what does this number or what do these numbers mean, right? So when you are doing reshape, you can specify how you want to reshape. So for example, I can decide I want to specify to reshape 3-1, but this will fail because when you are reshaping, essentially what you are saying is that I'm now reshaping this into 3 rows and 1 column, but you, you will lose some data because we have 20 rows and 1 column. So if you are reshaping the 3 rows and 1 column, you have lost data. So reshape does not allow you to change the shape to a new shape where the new shape will either lose some of the data or add empty values. because the total number of cells in 3.1 is 3, while the total number of cells in 20 is 20. So I can only reshape to a total dimension where the number of cells are the same as 20. So that means I can reshape to 10, 2, for example. 10, 2 is 20. If I reshape to 10, 2, you will now see that it has 10 rows and 2 columns, right? Of one is still the same as what it was. Okay, but this one, I have now reshaped it. It is now 10 rows and 2 columns. That's what reshape does. Then we can also reshape to 5 and 4. That's 5 rows and 4 columns. We're still maintaining 20 elements. So you can see it's reshaped 1, 2, 3, 4, 5, and 4 columns, 1, 2, 3, 4. I could also reshape it to 4, 5, which is 4 rows and 5 columns. Okay, so it's now 1, 2, 3, 4, 5 columns and 4 rows. I could also reshape it to the next one, has to be 2 and 10, right? Again, that will now give you 2 rows, 1, 2, and 10 columns. The columns start wrapping around. That's why you're now seeing it going this way. 1, 2, 3. And then we can reshape it to 1 and 20, which is a single row and 20 columns. In this case, you now see that it's almost looking the same as this because this one is also in a column format. So that is what reshape does. I could also do 20 and 1, and that will shape correctly. Now you notice that reshaping to 20 and 1 is the same thing as reshaping to -1 and 1. So what does a -1 now mean? The -1 means that if I don't know the number of one dimension, I can use -1 to represent it. So -1 in this case means anything that will make it fit, right? So just for me to demonstrate it again, if I do reshape 3 by 6, that's 18, right? But we have 20 elements, 20 times 1, so that will fail, right? And therefore, you can never reshape into something that has 20 elements. You can never reshape it into something that has 6 rows because there's no way you can. So think of it as a way of just reorganizing data, but you cannot lose and you cannot add. So with this, I could say, okay, let me reshape to 4. I want to reshape to 4 columns and whatever number of rows. So you see, -1, 4 is the same thing as having 5 rows. So the -1 always says pick the remaining multiplicand or whatever it's called that will allow us to maintain the same number of elements. So by the time you say -1 and 1, it means I want 1 column, and then this should be whatever number of rows will allow us to have 1 column. So I hope that kind of explains that. So essentially, think of -1 as a wildcard when you are doing reshape. Think of -1 as a wildcard. That means it can represent any number, but the number that will come out will be the number that best allows the alignment, based on what you reshaped. So I hope that helps as a kind of quick walkthrough on what reshape is. So effectively, when we reshape the vector, it becomes a matrix, right? So you still going to have the same dimension, the same number of rows because you are saying 20 data points, okay? And that's all you do. You reshape it and then you run fit, and it fits. It fits. That model is the linear model. Now, you have a linear model. Fit essentially trains the model on the data. It trains the model on the data. Remember, the data you supply is the X and Y. So the next thing now is to do prediction, right? Of course, one other thing you could do is to calculate, to do prediction. So you have trained the model. You see how easy it is. When we were doing it manually, we were using a loop. We had to choose learning rate and all kinds of things and all kinds of things. By the way, SKLM will choose some default learning rate. It will choose algorithms that, you know, are smart about learning rates. So it fits. This has trained the model. See how simple it is. The next thing now is to calculate my y hat, which are the predictions. So to calculate the y hat, you simply run model.predict, use the predict method, and then you specify the x values that you want to use to predict. So now I'm using the x values I used to train. It will now predict and give me the y hat values, which are the values that the model is predicting, right? That is different from y. Is the value, the true values that you are giving to the model to learn from, or you're training model on them. So with that now, we can then do that pie plot again. We do scatter first to scatter x and y. So this is giving us the original real data, right? I normally like to use, yeah. And then we use plot, which will give us a straight line. Why we're using a plot in this case is because the lines are correlated. You're using a model to, predict it. So by the time you plot the scatter holds the original data, while the plot holds the final, uh, value that the model has predicted. You can see that this model has done the prediction. So the training was just this single line here that says model.fit. That's how good sklearn is. And you see that it is really, really useful in a whole bunch of different things. So that is just simple linear regression. Now, we can do others. So let's do linear regression with multiple variables. This was linear regression with a single variable, right? So for us to do linear regression with multiple variables, I am going to again go and pull the data that we used for multiple variables last time. Okay, let me go look for it. We just did it now. Um, so while that is loading, I'm going to now move on. For us to do multivariable, you will still use the same linear regression class. You still use the same linear regression model. The only difference is that the X data that you are passing in is going to be much more. So here is the data that we are using now um, here's the data that we're now using for multiple variable linear regression. Okay, so if you look at this, we now have we have three x's, right? X1, X2, X3, and then we have y. Now, the thing is, when you are using linear regression, you actually have to stack them with, you only have one x, which is a matrix. So you can see that this there are three different x's, three different vectors. So in the other case, we actually had to do a reshape, right, to turn into a matrix. But here we are having the three x's, which represent the three different features, right, that we are training this model to be able to um, predict from. And then the y, which is so we'll first of all concatenate the three, right, the three of them into one x. And there are many ways to do that. You could use np.stack, right? And so np.stack is going to take these three and it will allow us to have a single array. So if you look at it, oh yeah, I need to run this. Okay. So if you run np.stack, you now see that there were three arrays of x's. I can put them here, x1, x2, x3, or three vectors. See, there are three of them, and they're all 20 of shape 20. I could also print their shape as well, their shapes. Okay. So if you look at all of these, you see they're all of shape, just a single vector of length 20. Now we stack the three of them, so we now have a single matrix that has 20 rows, which correspond to this 20, and three columns. I can also print the X so you see the X how it looks like, right? You can see that this X is now a matrix and is made up of these three in a row-wise arrangement. Now, you with this, we don't need to do any reshape because it already has a two-dimensional shape. So what you do is you can do a model again. So this model is now you can use a different name. We still use the same linear regression model, same model, even though not the same instance, right? This is another model. So maybe let me switch it so that we can understand that these are different. This is model 1D. So let's say one dimensional. Um, one dimension, that is a single um, linear regression, single variable linear regression. Then um, we now create another new instance of the same linear regression model type, right? But this one is a two-dimensional. And we fit it. We now fit it on XY. Of course, the XY is this new X and Y. The X is the 20 by 3, and the Y is, of course, this Y. Okay. And then you can run, you train it. Fit does the training. Now you have a fully trained model. See how fast that was. Now, the way I normally like to plot in this case, because here you now have this problem of how do I now plot? I could actually do a three-dimensional plot here, right? A 3D um, with XYZ, right? To show how the three correlate. But that's always very difficult to make sense of. So what I do instead is I will now plot, um, I'll plot a line of, I'll plot a scatter. So I now plot a scatter of Y and Y. The question is, why am I plotting Y against itself? Of course, it's going to be a straight line. So really, it's not, it shouldn't be a scatter, it should be a plot. So this is a straight line that says, okay, I'm plotting Y against itself. This is if your regression line, well, not regression line, but if your Y hat matches this line exactly, that means your Y hat is predicting the Y accurately. But if not, then we will plot a scatter of Y and Y hat, which is what we predicted. Okay, I did not do it here, but I can just predict. I can just do it at once. Model 2D dot predict. All right, I predict the X. Okay, and I want to make it red color so that we can see the difference. Just like we did red color when we're plotting this other one. So do color equals red. So when you plot this now, this is a different interpretation, right? It is different from this one, but it kind of gives the same story. In this one, it says, I'm drawing a straight line to predict this point. So this is how good my straight line is. But this one is saying that the straight line is actually the original true data that you're plotting against itself. I am now plotting how well my prediction is. So this shows you is a measure of how close the prediction is to the real values. And you can then do a mean square error. If you now want to do error evaluation with MSE, you now use the mean square error. And this mean squared. And you pass in the first value that you want to, the real value is a true value, which is Y, and then a predicted value, which is still the same thing that we did before. And you see that the mean squared error is 2.71. 69. So this is now linear regression with multiple variables. Now let's look at the logistic regression, which is something that we kind of had already done. Logistic regression is now you are using a decision boundary. Of course, we talked about vectorization. So you can see that all we just did now is vectorized. The X is a full thing. You don't even need to bother about vectorization anymore because sklearn has handled it all internally. So if we want to do logistic regression this time around, then you will do the same thing, right? You go and look for the logistic regression class, right? That sklearn provides to you. And your documentation actually allows you to easily find all of those, right? So again, you can now make a model, maybe logistic. It will be a logistic regression model. So let's import it first. I forgot. Okay, let me just import it here. You don't need to go all the way to the top. So you can import logistic regression still from the linear model. Then you just use the logistic regression. Okay. And then you fit it. Um, so you still have the X data and the Y data. Of course, I have to pull in the X and the Y data, which we used for the logistic regression problem last time. And we have it in a vectorized format. You can actually do logistic regression with any number of complex data, right? So so here's the data for logistic regression. If you look at it, the main difference, of course, is that the Y is just zeros and ones. You are doing classification, so they are not um, values, but they are labels effectively. So in the same way, you would concatenate the X and the Y. So you now have a single X that is NP dot stack on the columnar axis. If you now look at the X shape, if you look at the X shape, you will see that it is the number of columns, the number of rows here and two columns. So that's 50 by 2. Okay. And again, you just fit that. This time around, the Y is a small lower Y. And we have logistic regression. You have trained the model. You now have a trained model. You can then use this model to predict any value you want. But let's plot it in a curve. So to plot it again, we normally do a scatter, right? So typically you want to do a scatter of the y, which is the original value, and then the y hat, which is model logistics prediction. Okay. Um, we'll still use any color for this. So if you print this, you'll see, yeah, I've noticed something. So this is nice, but this is off because this shouldn't be here. Um, so probably we needed to do some more training on this, or maybe the data is difficult to fit. But the other way, a better way, this doesn't give us a very good view when it comes to classification problems. With classification problems, you want to plot a decision boundary. So the first thing you do is plot the values of X and Y with their colors. So that's how you can do that. So to do plotting the values of X and Y with their color, you do plots dot scatter. Um, well, let me leave this. I'll come back to that. So the values of X and Y will be, you plot the X1 and X2, and then the color will, you use the value of Y kind of to match the color. So this is a decision boundary. So you can see that here, um, the ones that are of this color, you could also choose a color and say it should be red, is red if Y. So you could also do something like this. C is red if Y, else blue. So this is if Y is true or if Y is zero. Um, yeah, I think it is. Oh yeah, that's yeah, correct. Uh, if you want to distinguish, you have to use a numpy. I forgot that this is this is a list, a numpy array. So you can't just do that. You have to um use a numpy else or if function to do that, which we can easily do. So anyway, why this is printing yellow for some and magenta for others is because the y has two values. It can be either 1 or 0. So when y is 0, it plots the x1 against x2. So the spatial position represents the x, right? While the color represents the y. So this is how we do classification, because then we now say, okay, this is a decision boundary. You could actually say that this is a decision boundary, right? This is the point. I say, okay, if it lies on this line, if it lies to the right of this line, then it is red, or it is true, it is yes. If it lies to the left of this line, then it is false. Okay, like I mentioned the other time. Okay, so the second thing then you would do is plot a decision boundary based on the prediction. So you're going to plot a correlation between X and Y. So it's good to do that so that we'll see. Um, Typically, for you to plot a decision boundary, you need to kind of plot the point at which the value would switch, right? So that requires a bit of maths. Um, so typically, the for a linear regression problem, this is what it would look like. It would look something like Um, let's see. So it will look something like W. So this is it. You're starting off with a linear equation, and the linear equation is y equals mx plus c. Okay. Now, for this kind of there are two features here. Okay. You have the x1 and you have the x2, and you have the y. So if you wanted to represent this, I'm just trying to explain how you can calculate decision boundary. So maybe I should put that here so that I can also explain what a decision boundary means. Decision boundary is the line at which the model will say, okay, when it is to the right of this line, it is red, and when it is to the left, it is right. So to calculate the decision boundary, the first thing is that the equation, the equation for a two feature, right, um, linear model, we're still using a linear model. It's two features, but we're still using a linear model, even though we're using a linear model. When you use a linear model for classification, that's why it's called logistic regression. You're still using a linear model, but you're using it for classification. So what you have is that the equation of y, which is the predicted value, is always something like this. It's always something like y equals, you could say m1 x1, right? Plus m2 x2 plus c, right? And the other thing, well, let me write it in the way that we use when we are, speaking of neural networks. So W1, which is weight 1 times x1, plus W2 x2 plus b. So you see notation kind of changes, but it is still the same thing, right? It's just change of the letters that you're using, the alphabets that you're using, right? So now the next question is, when you do that to solve for the point at which the it changes from 1 to 0, is to solve for when this equals to 0. So you solve for when y equals to 0, right? And if you do that, then you get W1 x1 plus W2 x2 plus b equals to 0. And you take this equation and you solve it and you plot it. That will give you the decision boundary. It's as simple as that. So the question is, um, how do we do that, right? So um, I'll show you how shortly. The first thing is you rewrite that equation so that you can make one of the parameters the subject of the equation, right? Um, Rather, not one of the parameters, one of the variable. So if you solve for x2, let's say we solve for x2 first. So that will give you x2 equals minus, if you just do this, right, essentially it's minus w1 minus w1, because you bring the other to w1 um, over w2, right, times, let me just type this in. I'll adjust this to mathematical notation very soon. Times x1, okay, minus b divided by w2. So you solve for x2. Once you do that, then you can easily plot that equation. So let's do this. let's do the code for this. So the code for this is, first of all, let's assume coefficient W, it is the model dot coefficient. So this is the way you can pull the parameters from the model. Remember, the model is a trained linear model. So this is model logistic. Sorry, trained logistic model. Well, it's still a linear model anyway. It's just that we're using it for classification. So let me show you a few things. This is a model itself. It doesn't have, it's an object. So, but you have the coefficients in there, which is an array of the parameters, essentially. And you can see that after solving for it, you have two parameters, the W1, which is 2.84, and the W2, which is minus 0.86. There should actually be a third parameter because let me see. This is okay. It's a two parameter. There should be a bias term. There should be a bias term. Okay, the bias term is on the intercept. So here are the two parameters, the two W's, the coefficients. That's why it's called coef, the coefficients of the independent variables, and then the bias term. So let me also put that here so you can see it as well. So if you look at this, you now see that the bias term, which is the C or the B in this case. So you have the W1 being the first number, W2 being the second number, and the intercept. This is for each column, for each set of features. Now, so you can then extract, right? So to extract, you can extract the coefficients and intercepts. So the coefficient will be the W. We're going to take the whole W as a single vector, right? And then we'll take the whole intercept as a single vector, which is the B. Okay. So that's the first thing, step one. Then after you do that, the next thing is we'll generate the X values across the data range. Okay. So to do this, we typically will choose a maximum value for X and a minimum value for X, right? And we will then use a linear space to extrapolate values in between, right? That's normally the approach. The other way is to generate for each single point one by one, but that's not very, very fast. So we'll start with the minimum value of X. The minimum value of X is X0 min, right? So this is the first value of X. Let me show you again so that you can understand what we are doing here. X0 is um, X0 is the combined X and Y values here. So X0 is the first row. Sorry, the first column, basically. The first column. Then so if you take that first column, remember X has two columns, X1 and X2, which we got by combining. Let me print it out so it's easy to see and understand. So you have X here. You can see X has two columns, 50 rows, two columns. So we take the first column, which is what this does is take the entire row, take all the rows and take one column. You need to go and study a little bit Python, on Python arrays and array indexing and array striding and all of that, right? We can do that in a separate thing, but I'll send a link or links to look at so that you understand what these things mean. But what this means basically is you are taking the full range of all the rows, but you're taking only column 0. which is the first column. So you get the first column, and that corresponds with this. So you take that first column and you take the smallest value in it, which is X mean, right? Then you also take that first column and you take the largest value in it. That's the X max. Okay. So that gives you all values of the first column of X, all values of the first column of X that you want to use to plot. So remember, you are plotting X, Y. So, or rather, you're plotting X1, X2. Another way is we could just do X1, X2. X1, X1 is also the first column of X. If you remember we got X by combining X1 and X2 by using stack. So X0, the first column of the big X, is the same thing as X1. So we can still use X1 here. If we don't want to do all of this, we can still use X1 here. We can still use X1 here. It's still, in which case it's actually simpler to call it X1 min and X1 max. So we get the values of X1. We want to plot these values of X1 against X2. Okay. That is what will give us a decision boundary. Now we can do what X1 line, which is np.linspace. So what linspace means is a linear space. So you are basically generating values in a linear space between spacing them linearly between the minimum value of X and the maximum value of X1, rather minimum value of X1, the maximum value of X1. The third number in this thing tells you the number of um, values you should extrapolate in between. Okay. So all of this is going to be a vector, which if you look at, you will see, you can see it's a single vector and it has 100 values in it. And those values start from the minimum value of X, which is minus 2 to the power of 0, to the maximum value of X, which is 2 to the power of 0. Right. It goes between 2.27. So it has 100 numbers that are uniformly spaced in that range. That's what lin space does. It gives you uniform spacing. You could actually plot it. Okay, but when you're plotting this X, you now use this X to generate the corresponding X2. So remember we had already derived the formula that we use to calculate X2, which is this. Okay. Um, so so let's use the formula, which is X2. Let's just take this and use it. Okay. That's the formula for calculating X2 based on X1. Okay, so we can now say X2 line, because you are plotting the whole X1 line, will now be W1 over W2. And W1 is the first weight, which is W0. And W2 is the second weight, which is W1. Okay. Times X1. All right. But this time is the whole line. Then minus B. B is the intercept. Okay. And divided by W2, which is the first one, which is W1. And that is the second set of values. So effectively, we have the first set of values and we have the second set of values. I can also print the second set of values here and you'll see them. So with this, the next thing you do is just plot the graph between those 2 points and you will have your decision boundary. It's going to be a straight line, right? So that this is actually step 3. Step 3, calculate the corresponding X2 values from the linear equation. And then the last one is number 4, plot the line, the decision boundary line. And it's not very hard, so plot. Yeah, so typically you first of all plot the scatter plot. This one we had already plotted, right? Which is the um how it looks like the scatter plot. Then we will now plot the we'll now plot the decision boundary, which is x1 and x2 line, and color it. So that's it. If we run this, so you can see we have the decision boundary here, this line. And you can see the decision boundary is able to classify. So anything that is above this line is classified with this color, right? And anything that's below this line is classified with this color. So, but you can see that this is not a perfect line. We could say, okay, let's adjust. Maybe we could have had a better line. Somebody could say, is it possible that we could have had a better line if maybe we drew the line like this? Because here you have some of the yellow crossing over onto the other one. So, but anyway, that's how you plot a decision boundary. Decision boundary is very, very useful. We'll do more of decision boundary when we go to SVM, which is the support vector machines. All right, so we have plotted this, right? Now, I think that kind of wraps up the our hands-on on regression and classification with sklearn. There is a lot more you can do, right? It's just that we don't have enough time. So let's look at other methods. So apart from the linear models, which we use and we have seen, there are a whole lot of other approaches that you can use for modeling data, right? The linear models, which we use for regression, linear regression, and logistic regression, are very simple. Like I've shown you, the decision boundary is a straight line. That's why it's a linear model. Whether you're using it, or if you're using for classification, it's a straight line. So there are some kind of data relationships that are too complex for you to be able to model with a straight line decision boundary. And then if it is regression, you are drawing a line of best fit. Your line of best fit is just a single straight line. Again, it can be very challenging for you to do proper fitting if you are using just a straight line. So you have other models and approaches. So we are going to talk about some of them. The first one is the decision tree. The decision tree, we'll go into a bit of detail on how decision trees work and the principles for them. But a decision tree, think of it like a flowchart. That's basically what it is. It's a model that follows a tree structure. It splits the data based on feature thresholds. So what you mean by feature threshold is that you give it a threshold and say, okay, if the value is greater than this, then you classify it as this, right? If the value of this feature is this, then you classify it as green. If the value of this particular feature is otherwise, you classify it as red, right? So that's kind of the basic. So think of it like a yes/no flowchart, where typically you come into the beginning at the top of a flowchart, you have a condition that says, is this or this true? If the answer is yes, then it branches off to this side. But if the answer is no, it branches off to this side. All right. That's why it's called a tree, because effectively what you are doing is that you are building an inverted tree, which is a standard data model in machine learning or in computer science generally is what we call a tree. So it's actually very easy for you to interpret because you see the basis of the choices. Of course, when you go to the next node, if you have another decision to make. That's why it's called decision trees. It's actually a tree, but a tree is built by making decisions. So when you get to this point, you have another decision to make. Is it this or that? If it is this, then it branches off this way. If it is that, it branches off this way. So at every node, you make a decision, and based on the outcome of the decision, you decide where you branch to. And you have so many different decisions at each point. So effectively, every node is a decision, and all of these decisions come together to form an inverted tree where the first node that you enter from, that's the root. And that's why it's an inverted tree, because the topmost one is a root, unlike in a natural tree where the root is at the bottom and the leaves are at the top. But in computer science, trees, the roots are at the top, and then leaves are these ones at the bottom that do not have any child. So the definition of a root in a tree structure is the node that doesn't have any parent. It is the first parent, and every other connection or relationship it has is a child of it, is coming out from it. While a leaf is a node that doesn't have any child. In other words, it doesn't have any relationship coming out of it. It just comes out of others. So it's very easy to look at this kind of data structure and interpret what it does. The only challenge with decision trees is that it's prone to overfitting if you don't prune it, right? Because you can have so many different options coming from it. The amount of note that every node essentially ends up corresponding to, think of it as a parameter because you are making a decision at that point, right? It's a choice. So you can have so many nodes, it overfits the data. So example use of decision trees is you want to predict whether to approve a loan based on customer attributes. What will you do? You take each of those customer attributes and you put a threshold and say, okay, what is the monthly turnover of this customer? If it is greater than this, then you can say yes, he can apply or is eligible. If it's no, that's all, right? Then the one that comes from that, you can then add other conditions and say, okay, um, how many years has the customer been banking? If it is more than 3 years, or if it's more than 6 months, then it is a yes. If it is less than 6 months, then it's a no, right? So you keep having that kind of thing where you keep making decisions. At the end of the day, you get to a point where the customer that gets to that leaf that meets all of those requirements will be the outcome, basically. So that's how decision trees work, and they're very, very useful for prediction. In fact, in the past, they have been very, very strong as models for machine learning. So the next one is random forest. A random forest is basically an ensemble of decision trees. Now, remember we said that decision tree can be prone to overfitting. So they solve that by using random forest, where you train on different subsets of the data and features. So when you eventually want to use a random forest, you now aggregate, you allow each tree in that forest to make its own prediction. Then you combine the outcome by combining the prediction of each tree. We'll talk about that in detail. Then we have what we call gradient boosting. So gradient boosting is used in random forests and decision trees. Is a method of applying gradient descent to train the tree. So what happens is that you build each tree sequentially, and then when you are building a new tree, you use that tree to um, adjust errors of previous trees. So just like for linear regression and so on, that we calculate errors by calculating loss, we can also calculate errors for decision trees. We'll look at that again in detail. And then for at every step, we will now use the next tree that we are building. We use it to counter the error of the previous one. Just like when you are using gradient descent, you are moving in the opposite direction to the gradient to reduce the total loss. When you build a new tree, you build it in such a way that it kind of goes in the opposite direction to the uh, accumulated error or total error or combined error of the previous trees. So that's how you build the random forest, and you end up with that's what ensures that you get very very good accuracy, improves generalization, reduces overfitting, and so on. And random forests have been shown with gradient boosting to achieve very good results, best results, state-of-the-art results, right? On tabular data, tabular data. These kinds of models are really good for when the amount of data you have is not much, right? So you can use that, for example, to predict customer churn, credit scoring, and so on. So we are going to look at that in detail later on. For the support vector machine, that's another method that we use for regression and classification as well. So support vector machine, SVM, constructs what we call a hyperplane that is used to separate classes in feature space. So support vector machines are very, very useful in high dimensional spaces. And they have what they call kernels, which are used, or kernel functions that are used in this. So we'll talk a bit more about it. So example use cases for SVMs are the text classification and image recognition. If you look at this, you actually see that um, this is one of those kind of problems where you cannot draw a linear decision boundary. It's not good enough. If I were to draw a straight line here, the straight line will be very useless, basically, as far as being a predictor, right? You cannot find a straight line that does not still include a lot of reds on the blue side and a lot of blues on the red side. It is difficult. What I just drew first is probably the best straight line that you can draw, right? So in this kind of problem, you cannot use a linear regression or linear logistic regression to classify, because logistic regression is basically a straight line, right? That is your decision boundary. So what we now use is the SVM. The SVM allows you to use what we call hyperplanes, which we'll talk about shortly. A hyperplane allows you to map a linear decision boundary or some other kinds of decision boundaries like quadratic, RBF, and so on, into another plane, so that when we eventually map data into that plane, it looks as if it is a nonlinear decision boundary. So we'll look at that shortly. Um, K-nearest neighbor is another algorithm or method that we can use for regression and classification. What this does is that it basically is what we call a lazy learner. You train it, it learns based on, it classifies, it's a way of classifying by looking at a data point and finding the nearest neighbors around it. Okay. And then the neighbor that is nearest to it, it will pick its own classification. So that's how it works. Again, I'm going to take us through some of these. K-nearest neighbor is very simple to interpret. It's very simple to understand. It's very simple to use, right? Its performance depends on the distance metric that you choose, and then the value of k. K is the number of nearest neighbors that you will pick when you are trying to determine what each data point should be classified as. So k-nearest neighbors are very good for classification recommender systems. A recommender system is a system, like we said, that looks at what other people have done and tells you, okay, other people that did this, other people that are like you, that chose this, also chose that. And then also for pattern recognition, different kinds of patterns, not complex patterns, but simple patterns. Then we have clustering and dimensionality reduction. We'll talk about those as well. K-means is a system, DB-scan, which the full meaning is density-based spatial clustering of applications with noise. We'll also look at that as well. K-means basically partitions data into clusters by minimizing the variance in between the clusters. And it eventually learns how to group by grouping clusters that are close to each other, while clusters that are far apart are grouped into separate groups. We'll talk about that more. DB-scan uses density, so it identifies the noise and is able to handle arbitrary shaped clusters. For k-means, you would need to specify the k, which is like the number of elements that should be in a cluster. But DB-scan, you don't need to do that. Then dimensionality reduction is one other thing that you can do with these models. So principal component analysis. If we have some time, we can look at that as well. But like I said, it helps you to transform data in a multi-dimensional space into a smaller dimensional space, like three-dimensional space, for the purposes of visualization. So it's easy for you to plot the graph and see what the graph looks like, even though it's not an exact representation, but it's close enough. Or for noise reduction, and also for speeding up model training, especially by removing dimensions that don't really, features. A dimension is basically, um, think of it like a feature. If you have n dimensions in your data, it means you have n features. Again, I'll go into a bit of that. So let's talk a little bit about decision trees and how, it works. I've already kind of explained it intuitively, right? But if you want to look at it from a mathematical problem formulation, you can look at it as you have a data set, okay? That data set, of course, as usual, is made up of X values and Y values. And remember, I said this I represents each data point in that data set. And you have N data points from 1 to N, right? Where each X is a real number. That's what this means. It's an element of the real number set. Okay, so it's a real number essentially. And it contains categorical features. So this P means it is a real number that is partitioned, kind of. Okay, so what do I mean by partition? It is in categories, right? It is in a category that has classes or categorical features. So the X has categorical features. So we talked about that a bit last week or two, where we said, let's assume you have a feature and you can categorize those features. So for example, color of your eyes. The color of the eyes is categorical. So you can say it's black eyes, brown eyes, blue eyes, green eyes, and so on, right? They are not infinite numbers, right? But they are classes. So that's what it means. It means that each X has uh, features that are categorical because that's where decision trees really work. Because that's where you now go to that decision node and say, okay, does he have blue eyes? If yes, go here. Does he have green eyes? And so on. You cannot categorize if it is not in a category. You cannot do that decision. If you cannot do, if the value that you are trying to decide on is not categorical, then you have to convert it into a category by using thresholds. So by saying, okay, if it is age now, that is an infinite continuous space of values, right? Then you solve that by categorizing it or by bucketing it, like we talked about. You can say, okay, if the age is greater than, or if the age is less than 3, you categorize that person as um, a um, a child. If it's less than or a toddler, if it's less than 8, a child, and so on and so forth. So, but the main thing is that every X has to have features that you can bucket that way, or is inherently already categorical. Then the Y, of course, is normal Y, is a label, is a target. That's what you want to train on. So you can use decision trees to solve classification problems because in that case, if your Y has to be in a class, right? And it's often binary, true or false, 0 or 1, yes or no, and so on. But if you're using decision trees to solve a regression problem, that means the value of Y has to be a real number. That's what this stylized R means, is in the set of real numbers. This thing is not epsilon. It just means it's an element of a set. So Y is a real number. Um, in which case you're going to use thresholds to bucket it. So with decision trees, what you want to be able to do is to train or learn a function. The model is the decision tree itself, and you want it to learn a function so I can predict Y with low expected loss. Okay, and we'll see how we'll calculate the loss. You have squared error for regression, and then you have We'll talk about that. So the decision tree and random forest is a specific form of f of x. But this is a general thing for all models. A model is basically a function that you learn to be able to predict the data. That's essentially what a model is. And with linear models, a function is a linear function, right? Y equals mx plus c, and so on. So what the decision tree does is that it partitions the input space into axis aligned regions. So this is very big jargon that basically means the input space is the features, the data that's coming in as input, the features in that data. Partitioning means you now separate the data points based on which classification or category that the specific features that you're looking at belong to. As simple as that. And if it is a inherently categorical type of feature, you use a class label, like we said, red eyes, blue eyes, green, and so on, black, brown. But if it is a numeric value like age, then you bucket it. So that way you are classifying into region. So it's a sequence of yes, no questions, as simple as that. Well, sometimes it's not yes, no questions, because sometimes the outcome might be multiple outcomes if it is multi-category. But for the sake of simplicity, let's just go with only two categories, a binary tree, what we call a binary tree or binary search tree. So you're going to have either of two values for each feature. So you now have an internal node, right? I'll show you shortly. Internal node, you test on a particular feature. If it is numerical, you use a threshold. The threshold is T to check whether each data point xj is less than that feature value is less than T or is less than or equal to T. And then you put it in one bucket. If it is greater than T, you put it in another bucket. But if it's not a numerical feature, it is categorical, then the feature should be in the set of all the possible classes of that category. So that's an internal node. So an internal node always has input and has output. A root node does not have a parent. Okay, let me rephrase that because a root node has to have input, the initial input. But an internal node will have parents and children. A root node will not have parents, but will have children. The leaves will have parents, but they will not have children. So at the end of the day, the leaves become the prediction. By the time you get to the leaf, that should match a value of y that you're trying to predict. So because that trees are easy to interpret, just follow the branch and you see why the prediction was made. This is a good example of a decision tree. If you look at this now, so let's assume we want to do a prediction of the weather. So this is a good example of should I go out of the house today kind of prediction. Okay. So based on the weather. So you start off with the first feature of the weather, which is the windiness. Is it windy? If it is true, you take it this way. If it is false, you go this way. Now, if it is true, then you have to check the outlook, right, of the windiness. And the outlook, is it going to be sunny or is it going to be overcast or is it going to be rainy? If the outlook is future weather, how it will look like. Yes, currently it is windy, but in future, will it stop being windy? Will it become sunny? Or will it stay overcast? Or will it be rainy? If it is rainy, then the answer is no. I cannot go out, right? But if the outlook is overcast, I can go out, yes. But if the outlook is sunny, then there's another point of decision we have to make here. Is the humidity going to be high or low? If it is less than 83, we consider it as low, then yes, I can go out. But if it is greater than 83, then consider it as high, then no, I cannot go out. So this is how decision tree, that's why it's a decision tree. At each point you're making a decision. And the final prediction is in the leaf node, right? But depends on the sequence that you pass through to get there. On this other side, if wind is false, Then the only thing I need to check is the temperature. Is the temperature, above 83? If no, then I can't go out. It will be too hot. Is it less than 83? Then yes, I can go out. So this is a very good decision tree for should I go out today, right? Kind of prediction. So this is just an example. So the question now is, if you have that, how do you train a model? So the idea for training a decision tree model is you build a tree by recursive binary partitioning. What I just did now, right? We'll now encode it in write code around it, right? Start with all the training data in the root. Okay. The root is the first node that you check. So the first feature or the first condition that you check, that's a root. Okay. So you start with all the training data in the root. Then there's what we call when you go into a current node, there's what we call candidate splits. So candidate splits are look at some features and then pick a threshold. Okay. Then for each of those candidate splits, you're not going to train on all the data. You're just going to take some. You typically split it into into batches. Think of it as batching. You take that and then you compute a score, right? And then when you compute the score, there's what we call impurity or loss, which we'll talk about. That score is called impurity. That score will tell you how why it's called impurity is how pure is the prediction, based on that score. Okay. So what you now want to do is you want to choose a split that maximizes the impurity reduction. You want to have your impurity to be as high as possible. So you want to reduce impurity at each split. Okay. Or equivalent, you minimize the weighted impurity of children. If you minimize the impurity of children, that means you are maximizing the reduction of the impurity because you want the impurity to be as small as possible. And then you continue to do that recursively until you get a stopping condition. Just like we did a training loop, you continue to do that until you meet a stopping condition, which is you have a pure node. I'll define what a pure node is, but a pure node is a node where all the outcome from it are all in the same category, basically, right? That's one. Or the other one is minimum samples or max depth. Then you can also prune. So this is called a greedy algorithm. So I'm going to try to explain all of what I said. If you look at this, you have a decision tree here, and you have entropy. Entropy is called information gain. It's basically a measure of how much additional information, how much the features that additional information you have gained is essentially then you have what we call the impurity, the Gini impurity, which is a measure of how much from a particular branch like this, how much of them are in a particular category and how much are in the other category. So you always want to get to pure, which means you maximize the category. I'm going to bring us to see a Jupyter notebook on that. Okay, so these are the formulas. I won't dwell too much on this, but in summary, you calculate entropy gain by calculating the probability of K, where K is the number of items that you select for a split, right? And so probability for each item times the log to base 2 probability. If you can remember, this looks like what we use when we're calculating cross entropy. So that's why it's called entropy. It's still the same thing, right? It's still the same formula, which is like it's a measure of additional information. Entropy is something that is quite interesting, but unfortunately, I don't have enough time to dwell into it. But if you remember that binary cross entropy we did, this is it basically, and essentially this is also the way you calculate what we call categorical cross entropy, and it's just a measure of how far away am I from what I want to be or where I want to be. So that is the entropy that you calculate. You see the negative sign because of the log. Then you now calculate the delta H, which is the information gain from a particular split. So let's say you split some samples, SL and SR. SL are the samples that you have split to the left side of the branching. You branch into two, right? You can see that each of these is branching into two. So you branch into two. The SL is the samples on the left-hand side, and the SR is refers to the samples on the right-hand side, or the splits on the right-hand side. So if you look at this, for example, we have a total number of 6499 samples, and you can see that there's a split. So here you now have 3660 on this side and 2839 on this side. If you add this two, you see I have a total of this, right? So the value is calculated based on how much percentage of the samples on this side meets the prediction, right? The predicted value. And how many of the samples on this side meets the predicted value. So remember, it's binary, true or false. So how many on this eventually end up being true, and how many of this eventually end up being false? So that's the process it goes through. I have a notebook that I'll use to show that. Then you just keep going that way until you get to the leaf node. This is a good example of a leaf node that is pure, because you can see that there is no value on this side. There is no sample that falls into this other category, the right-hand category. We have 401 that fall into the left-hand category. So you always want to keep doing until you maximize the or you minimize the impurity. Okay. So the Gini impurity is a measure of that impurity, and you can see the formula is 1 minus the sum of the pK, right, which is a proportion of a class in that set. So here pK is like, if you have, basically pK is how much of it is on the particular side of the decision tree that I want it to be. So that's how we do classification. For regression, you use mean square error as your just like linear regression, you use mean square error to calculate, which is basically the predicted value, the actual value minus the predicted value. Okay, for particular set of values in that given node. So now the question is, how do you do the split? There are two ways. Like I said, the first one, you use numerical values. You sort the values, and then you can use a threshold to separate them. So anyone that is greater than threshold will be on one side, and anyone that is less will be in the other side, the other category. But for categorical, you can partition the categories if there are few, right? Or order them by target statistics and treat them like numeric. Then stopping criteria and pruning. So stopping can be minimum samples per leaf, or maximum depth, or number of splits. So we have pruning. If the tree is getting too large, you can drop off some of the branches, especially the branches that are not very meaningful. And there's also an algorithm to decide what branch to prune off or not. Complexity is just a way to calculate how, um, how long it will take, right, for you to do splitting. It's what we call O complexity. It's a matter of the, I don't want to use a complexity again word, but it is a measure of how well the algorithm does, how fast it performs. All right. Now let's just look at some real examples, very simple examples to help us understand. Let's assume that you have 4 data points. This I is a serial number. Yeah, 1, 2, 3, 4. For the I, you have X is the actual value. So in this case, we have just single feature X, and we have Y, the single outcome that we want to predict. And we have four possible data points, 4 values for X, 1, 2, 3, 4. So when X is 1 or 2, the value of Y is 0. And when X is 3 or 4, the value of Y is 1. So following this process, we'll first of all say, okay, let's look at possible thresholds. There are three possible thresholds we can use. We can either use 1.5. The thresholds are used for partitioning the inputs, the X values, right? The Y values are already clear. They are categorical. They are the labels. But the X values, we need to know how to partition which one should go to the left and which one should go to the right. So we can choose between any of these three values. Okay. So when we pick a value, okay, let's assume that yeah, the parent node has two zeros and two ones, which is here. That's obvious. Now, because the parent node has two zeros and two ones, the class proportion, basically the proportion that are zero is half, is 0.5. And the proportion that are one is also half. So that's what the PK means in what I was trying to explain here, right? So half of the outcomes are zeros and half of the outcomes are one. So P0 is 0.5. That's P0, P with zero outcome and P with one outcome, 0.5. So to now calculate the entropy, okay, in the parent node, remember the parent node is the first node that you make the first decision. You now use the entropy formula. So if you go back to the entropy formula, you remember the entropy formula is sum of pk times log to base 2 of pk, the same pk, right? So the first pk is 0.5, 0.5. So it's going to be 0.5 times log to base 2 of 0.5. And then second pk, which is p1, is also 0.5. So 0.5 times log to base 2 of 0.5. So you're going to have two of those. You sum it all, and then you apply a negative sign. So that's what we are doing here. 0.5 times log to base 2 of 0.5. That's the first pk, which is p0. And the second pk also, which is p1, right? 0.5 times log to base 2 of 0.5. So, of course, we apply a negative sign. So this is calculated, and you have a value of 1. That 1 is the value of the entropy. Log to base 2 of 0.5. 0.5 is 1 over 2. Is 1 over 2, right? Which is 2 raised to the power minus 1. So log of 2 raised to the power minus 1 to base 2 is minus 1. Minus 1 times 0.5 is 0.5. Same thing here. This is 0.5 plus 0.5. So 0.5 plus 0.5 gives you 1. And you see that's the value. That's why we are putting the negative sign, because we are looking at proportions. So proportions will always be less than 1, and the log will always be negative. So you use the negation sign to bring it back. So you have entropy of 1. Then you calculate the Gini impurity. The Gini impurity function is sum of 1 minus the square of the proportion for each of them. So since we have two proportions, we have two classes, true and false. The first one is 0.5, sorry, 1 and 0, or 0 and 1. The first one is 0.5. So square of 0.5 is 0.25. Okay. The second one is also 0.5. Square of it is 0.25. So when you add those two, you still get 0.5 back as the sum here. So 1 minus 0.5 is 0.5. So the Gini impurity is 0.5. So that's a measure of that. So that's how we are getting this 1 minus 0.5 squared plus 0.5 squared. That gives us this. So now, this is the initial calculation based on these proportions for the proportion, the distribution of the data in the Y. So we now go to the X, the input that comes in. If we are using a threshold of 2.5, then 2.5 will split it at this point, because it means above, if it's higher than 2.5, it's greater than 2.5, you have two numbers that will fit. If it's less than 2.5, you have two numbers that will fit. That's 1 and 2. So the left side, where X is less than or equal to 2.5, you have items 1 and 2, right? And the labels for them are both 0. So you can see that's pure, because why it's pure is that all the labels in that section are the same category. There's no mixing. So the entropy for a threshold of 2.5 will be HL 0 and Gini 0, simply because it's pure. The reason why that is you still have two pKs. In that case, the P0 is 1. Everything, the proportion of P that is 0 is 1. The proportion of P that is 1 is 0. That is, the proportion of P that has a value of 0 is 1, while the proportion of P that has a value of 1 is 0. If your threshold is, um, let me draw this so that it's easier to understand. So if your threshold here is, this is your threshold of 2.5, right? So if you're having a threshold of 2.5, then basically what we are saying is um, everything up here is to the left and everything down here is to the right. So if everything up here is to the left, then um, it's a pure, it's pure because everything, the classification is all one value, it's not mixed. Okay. So that's why the entropy is 0, because the entropy is basically, if you go by this same formula that we just did, you find that P0, which is a P that has zeros, is 1. Everything is a 0, so it's 1. I hope that is not confusing. And P1 is 0. Everything that is a 1 is 0. There's no 1 in this set. So if you do this calculation with that, you are going to get a HL of 0. That's the entropy on the left side. And then you get a Gini impurity of 0 as well. Then for the right side, where X is greater than 2.5, that's this side down here, you now see that items 3 and 4 are also labeled 1. So it's also a pure set because everything is 1. There's no zeros mixed in here, right? Everything here is 1. So if you now calculate entropy of the right-hand side, right? P0 is 0 and P1 is 1. So again, if you use the calculation for entropy, the value will be 0 because it is, remember, it is sum of pk log pk. So 0 log 0 is 0. Anything times 0 is 0. Then 1 log 1 is 0 because log of 1 is 0, right? So again, 1 times 0 is 0. So that's why you get zeros all through. So when you now do that, the information gain is going to be the sum, which is 1 minus 0. Information gain is, let's go back so that you can see what the information gain is 1. The formula for information gain is HS is the change, right? Is delta H, which is the change in the entropy. So the original entropy minus left entropy minus right entropy. Original entropy minus left entropy minus right entropy, or the proportion of the entropy, the left entropy, and the proportion of the right entropy. So if you go look at this again, you find that, of course, the original entropy is 1, which we have here. Then the left entropy is 0, the right entropy is 0. So 1 minus 0 is 0. And that's how you get that. So the Gini reduction is 0.5. Gini reduction is the original Gini minus the combined Gini of the two. The original Gini is 0. The current Gini is 0.5. So that gives you 0. Sorry, the current Gini is 0. So that gives you 0.5. So what this tells you is that you have the best split at 2.5. You can actually do this same calculation for a split at 1.5 and 3.5. And I'll leave that to you to do as an assignment, right? And then you come and tell me, you will find that um, the values are higher. This is a 1.5 split. So the thing is that with a 1.5 split, if you split at 1.5, yes, you have a pure set on the left, right, where X is less than 2.5, but you are going to have an impure set on the right because you have a 0 here, right? This is the this, but you have a 0, and this 0 makes this set impure. But this one is pure because you only have 0 here, but here you have 0 mixing it with the ones. Same thing with 3.5. If you have your decision boundary or threshold rather at 3.5 value of X. So that's basically kind of very simple data that we use to explain some of these concepts. But of course, in real life, things are far more complicated. Then we have random forest. So random forest is an ensemble of decision trees built using randomness so that the trees are roughly independent. So predictions are aggregated. And what happens in a random forest is that you have multiple decision trees that you have trained, and then you put them in parallel. So when you have a data set you want to make a prediction on, each tree in the forest will make its own prediction, right? And then you now aggregate the prediction. And this is the rule for aggregating the predictions. The rule for aggregating the predictions are, if you are doing a classification problem, then you take the majority votes. So if you have 10 random, if you have 10 trees in the random forest, and five of them predicted yes, and four of them, and sorry, six of them predicted yes, and four of them predicted no, then the aggregate prediction is a yes. You're just taking simple majority vote. Okay, that's what that means. But if you're doing a regression, if you're using the random forest to do a regression problem, then you again take the same input and you pass through each of the trained decision trees in that forest. And then the output, the prediction that you take as a prediction of the forest is the average of each prediction. So let's assume you had five trees and one of them had three, the other one had two, the other one had eight, the other one had six, the other one had five. You take the average of those values to give you value. Remember, regression is predicting a value, while classification is predicting a category or class. So the benefit of using random forest is that with a random forest, uh, you can have better generalization because a single tree has low bias. We'll talk about bias and variance later on. But bias is basically the ability of a model to predict the data correctly. So if you have low bias, right, it means that it is able to predict very well, right? If you have high bias, it means the model is not complex enough, it's not good enough, it's not big enough, it doesn't have enough parameters to predict the data and the features. But if you have variance, high variance typically means that the model is too large for the data and will overfit. If you have low variance, it means the model is good enough and should be okay. We'll talk more about that. So the idea behind random forest is that you train multiple uncorrelated trees, basically multiple uncorrelated estimators. Why they are uncorrelated is because you are not training them on the same data, you are training them on subsets of a data set, but you shuffle the subset very well, you separate them, and then you train each tree on its own subset. So they kind of learn. And then when you now want to predict, they have a lot of data that they did not see, so they will not overfit. Because typically decision trees overfit. That's why they have high variance. High variance means they overfit. And it's always good in that case to have a large amount of training data, but also keep behind a large amount of test data. So we'll talk more about the principles behind this. Okay, so that's a random forest basically, and this is just a visualization of it. So like I say, you have a data set of data. You now have, in this case, three decision trees. Well, you have actually n number of decision trees. It's just the three dots here, dot, dot, dot means you can have any number of decision trees in between. You train these decision trees on multiple data. You can see that the blue are the points of predicting one class, and the green is predicting another class. For the same data set, this one is predicting, these three are predicting blue, while this one is predicting green in this particular tree, right? Um, so, and it's very interesting to see that. So in this decision tree, you have only one predicting green at this edge and these three predicting blue. But you have another decision tree that you train on another set of data. Of course, here you still have three, but the three are another different three that are predicting. Okay, so you have another leaf node here, which I forgot. So you have 1, 2, 3, 4 predicting blue, leaf nodes, and then this one predicting green. While here you have also 1, 2, 3, 4 leaf nodes here predicting blue, while you have one predicting green, but this one is a different one. And you have so many like that. And then you have this last one where all of them are predicting, okay, 4 down here predicting blue, and this is predicting green. So what you now do is you will now do averaging to get the total, if it is classification, you do majority voting. So you pick the number. So if we were to look at this, then we would go with blue because here blue, if you want to add a total number of blue votes and green votes, right? Um, but if you're going with averaging for a regression problem where you are predicting a specific number, then you would average the values. So this is a very good visualization of how random forests work. So this is kind of how you train it. You start off with a large data set. You take a sample, what we call a bootstrap sample. So you look at the number of trees that you want to train or that you have. So you have to have each subsample or subset needs to be small enough to be separate, but to be able to have enough different data sets for all the trees. Then for each sub sample of the data set that you take from the original training set, you now train a decision tree on that data set with only one modification. And the modification is that you select the best split from a random subset of M features. So in other words, you're not going to train from all the features in the data set, but only from a number of features, a subset of it. And then these are how you can select the features. You can either use a square root. This is absolute value of square root or absolute value of P over 3. So remember what P is. P is proportion that is in a particular um, set, right? Or of a particular outcome or a particular category. And that's how you do it. Just keep training it. Uh, as you're training a tree, it's growing to full depth. So you don't prune it. And you just keep doing that. Then when you want to predict, like we said, this is just a mathematical representation of what I just said. Mode means the highest vote, effectively, the highest vote, where TB is the outcome for each tree. TB is each tree. T means tree. So for each tree, it does a prediction. Um, and the B, you have to use different data sets. So you take the one with the highest vote. Regression, you take the average, which is the sum divided by the number. So that's how you train random forest. And then there's a whole of other thing. There's what we call out of bag error. For each training sample, a fraction of the trees did not include in their bootstrap sample, right? So use those trees to predict X and compare to true Y, averaging over I. So because when you're training with a training sample, you always hold back a certain amount of data. So that's what they're just talking about here. And then you use that just like you have training data separated from test data in the same way. Uh, so I'm not going to go into bias and variance yet, even though it really matters with decision trees and random forest, right? But I think is what I've kind of said already. Low bias means it knows it has enough capability or capacity to learn the data set you give to it and predict well, correctly. But low bias can also become high variance. High variance means it begins to overfit on that data, so it does not generalize. Overfitting means it only learns how to predict that data very well, but you give it another data or a separate data set, it is incapable of predicting it properly. Yeah, so this is how you can train a tree. I have a notebook for this. This is how you can train a random forest. If you were doing it, you know, yourself, okay, by calculating or by going through the loop, but we won't do that, right? Rather, we will just use sklearn, okay? And to use sklearn, see how simple it is. All of these things I talked about were theoretical for you to understand what is going on. But and I think you can go try out how to do a simple decision tree. But I think the best thing is just use a decision tree classifier or use a random forest classifier. And that's it. Then you specify all of these parameters. So that's how simple it is. to do with sklearn. And that's why we say sklearn really helps a lot because sklearn has simplified. There's a lot of maths going on with decision trees, and we've not even talked about support vector machines, which we'll talk about when we meet um, next. But this single simple function call here, random forest, then fit. There's a lot of maths, and I really needed us to see what all of this is. So yeah, so this helps you to understand some of the parameters that you have to pass in. So for example, max depth, this is the maximum depth of the tree, right? So when we say depth of the tree, let me go back to show you graphically what that means. So when you say depth of the tree, if you look at this tree, for example, this tree has a depth of 1, 2, 3, 4 because it has 4 layers. You go down 4 nodes to before you get to it. 1, 2, 3, 4. So this one has 4, 4. This leaf has a depth of 4. This has a depth of 4. This leaf has a depth of 1, 2, 3 of 3. This leaf has a depth of 4, 4 and 3. So that's what max depth means. If the depth of your tree is too much, it will overfit. So it's a good idea to balance it. Okay. Then criterion is Gini. So this is a criterion that you use for calculating loss, right? In machine learning, it is called criterion. And you see the same thing even when we are using PyTorch. So Gini is Gini impurity. There are a bunch of other criteria that you can use for determining the loss or the cost. The mean sample sleeve basically is saying the minimum number of samples that you will use in the leaf nodes. Okay, so these are all parameters you can use to fine tune or adjust the behavior of your classifier. Now, for random forest classifier, the parameters you pass is n estimator. That's the number of decision trees that you have in that random forest. You can see here is 200. That's a lot. So that's why random forest gets better because you have a lot of decision trees, each of them making a decision, and then you aggregate that decision either by using the simple majority vote for classification. In this case, you're going to use simple majority vote, or you use average for regression problem. Then max feature is a maximum, how you determine the maximum number of features that you withhold or that you use for training each tree. If you remember, I gave two options here. There was option of using a square root, right? Square root of a proportion, and you also had p over 3. So you can use any of those two. And then mean samples leave. Then max features means m is square root of p, like I said. OOB score is if you want to use OOB for error estimation as well. Now, so if you look at it, you have strengths and weaknesses of decision trees. Decision trees are the main strength that is interpretable. You can actually look at the tree, how it's created, and you can understand how the model arrived at a particular answer. It's very good at handling numeric and categorical features. It requires very little data pre-processing. It captures non-linearities very well and feature interaction, and it has fast inference because you're just doing if statements, basically. But the weaknesses are it has high variance, it can overfit. The decisions are axis aligned, right? No oblique splits. I will talk about that. And it can be unstable to data perturbations. Random forest is very, very good out of the box. It's very robust. It can handle large feature spaces because, of course, you are combining lots of decision trees in parallel. It's very resistant to overfitting. It generalizes very well. And you can also include the OB error to calculate your error better. The weaknesses are that it's less interpretable because it's an ensemble of many trees. It takes longer to calculate and give you an answer because there are so many trees. And it can struggle with very high dimensional sparse data, And then it also is biased when data has strong class imbalance. So what we mean by strong class imbalance is that there are some data where a particular class has much more proportion of data than others. A good example is if you're using it for medical prediction, and you want to predict those that have, for example, cancer, and you have a data set, you find that most of the data set, they will not have cancer, it will be benign. Tumors will be benign mostly, maybe 90%, and then 10% are non-benign or malignant. That is imbalance. You have so much more data in one class or category than in the other, right? So for you to solve that problem, you have to use class weighting or balanced sampling. So then the hyperparameters you can tune with decision trees: max depth, mean sample split, mean samples leave, max features, the criterion, whether you're using Gini or using entropy, the number of estimators, if it's a random forest, which is the number of trees, right? The more trees you have, the more the variance. Maximum number of features, um, maximum depth, bootstrap, and OOB score, right? So advanced other things you can look at. We didn't look at gradient boosting, HG boost, but like I said, gradient boosting is a variant of gradient descent that is used for decision trees and random forest. Basically, you are creating trees in sequence. So in that random forest of 200 trees, you don't create all of them at once. You create them in sequence, maybe in batches. And as you are getting your error loss, either with Gini impurity or entropy or whatever, you calculate your error. You train the next batch or the next tree in the opposite direction, kind of in a way to minimize that loss. So that's what gradient boosting is basically. Yeah. So there's a whole other advanced things that we can talk about. Extra trees where you can choose your split threshold. Remember the threshold for splitting? When we're talking about 1.5, 2.5, 3.5, pick best among them. So that means you're not using the same threshold for the trees. Each tree you use a different threshold, right? Or you randomly choose threshold among the trees. So the trees are not the same, and then you can pick amongst them. So this is kind of a way to figure out the best threshold if it is not very obvious. Um, then oblique trees is where you have linear combination of features, right? So oblique trees are more flexible, but all of this is less easy for you to look at the algorithm and see what it does. But again, all of these are mostly theoretical stuff. At the end of the day, yes, you can actually go and try to do some kind of um, maybe decision tree, right? But it's easier for you to just use sklearn. So this class is really to help you understand the decision trees. It's not really for you to be able to build them from scratch. But as an exercise, if you want to go further in, you know, in it, you can actually do this. And I would still support it and say, okay, yeah, go ahead and see if you can do decision trees, right? So this is a Jupyter notebook on decision trees and random forest, right? This is all of what I explained in the PowerPoint. You will see all of the equations here. And I can show you this for you to study. This is if you wanted to do decision tree by hand, basically. So you see, this is how you calculate the Gini impurity, right? You count, and then you calculate the number that are in one particular class. This counter, what it does is it takes any value, like we were talking about 0011, right? And the zeros, there are two of them, and the ones, there are two of them. So those are the labels. So you use that to calculate the Gini impurity for any particular number of things in a particular set. Then you can split data set. You choose the threshold. You specify the feature you want to split, right? And Then best split is to essentially training the tree to find which split point gives you the lowest gain impurity. So you are going to keep adjusting the split point until you get the lowest impurity. Of course, for this very simple problem where we had only four data points, the 0011, it's even easy for you to just see visually where to split. It's 2.5. But there are some data sets that is a lot of data, so it's not easy for you to see immediately. And there are a lot of features, so it's also not easy to see immediately. So in that situation, you can use this kind of algorithm. And what this is basically doing is you split the data set. You now have X left, Y left, X right, Y right. So you have the X values on the left of the split and the X values on the right of the split. Then you also have the Y values on the left of the split and the Y values. Okay. And if any of the Y values is 0, that means you have reached maximum purity, right? One of them is 0. So the other one is the only item. So you end, right? But if not, then you can calculate the proportion on the left. The proportion on the left is the number of a particular Y that on the left divided by the total Y. And the proportion on the right is the opposite. So you can just get that by 1 minus P. So that gives you proportion on the left, proportion on the right. Then you calculate the Gini impurity, which is the proportion on the left times the Gini impurity of the Y on the left. Okay. And this Gini impurity, remember, was a log. Well, okay, in this case, not log. We are using a count to calculate it. And the impurity, oh, the impurity, the total impurity, sorry, I mixed up. The total impurity is the impurity on the left times the proportion on the left plus the impurity on the right times the proportion on the right. So it's kind of a weighted average of the impurity on the left and the right. So that gives you the impurity for this particular direction. If this impurity is less than the best impurity, then you will now keep this as the best impurity value, the best feature, and the best threshold. So you're tracking the best impurity, the best feature, and the best threshold. And you're just going to go through all of the features for that single node. You are calculating this for a single node, best split for a single node. So when you are done, you now come up with the value that you have saved as the best feature and the best threshold. That is what you will now return. So that's how those are some of the basic calculations you do. Then you now have a tree node. This is now representing that tree structure that I talked about. And you now build a tree. Um, this is the algorithm for it. And the steps are kind of like what I said. You check the depth. If you are above the maximum depth, then you stop, right? And you return the tree that you have. Then this is kind of recursive. So what is going to happen is that you will take a random subset of the features, okay? Um, Depending on if you have max features or not. So you take a random subset of the features. Then when you have taken a random subset of those features, you now use that best split algorithm we just looked at now to choose the best split point. So like I said, if it was a small set of numbers, you can even visually see what the best split point is. But in this case, you use this algorithm to get the best split point. Um, then once you have gotten the best split points, right? If feature is none, that there's no valid split point, that means you have ended at that point. But once you get the best split point, you split the data set based on that threshold that marks that split point. And when you split the data set, then you now build the tree on the left side. So you build a tree on the left side um, using the values that were on the left. In other words, remember when I did this, let me show you. I said the split point, you have a split point, you choose the values on the left to build and the values on the right to build on the right. That was here, right? So you you allocate these two to the right and these two to the, sorry, these two up here to the left because it's less than, and these two down here to the right because it's greater than. So, and that's basically that principle. You keep doing it that way until you get to a point where you now have your predictions at the trees. So you have built one tree, and then after that, you will do another one. And when you're finished building a tree, you can then use that tree to make predictions. And the way to predict is just to keep going down the tree from the roots, following the thresholds based on the value that you have as your input. And then you get to whatever prediction you have at the end of the tree, right? And that value you have at the end of the tree, um, that's the prediction. And that's it. It's actually quite simple. The interesting thing is how can the mathematical formulation makes it look difficult. But if you have done a flowchart before, right, take a problem and use a flowchart, that's what it is. So we're just turning it into a mathematical algorithm, into a computer algorithm that we can run in a computer. But intuitively, it is something that we would even do without thinking. So random forest effectively is kind of the same thing. Well, not the same thing. Random forest is different in that you are taking multiple trees and you train each tree separately. So when you're training a random forest, you start off with an empty set of trees. You determine how many features that you want to use for training. You determine how many each tree will get. And then for each of n estimators, you will train a tree. So you can see here, you train a tree. Um, you select data for that tree, a subset of data for that tree, and then you use this decision tree, train a tree. And when you're done training the tree, which is what tree.fit does basically, that we've already done that up here, right? The tree.fit, which does this, which basically builds the tree. So um you append it. So when you have finished training all the trees or building out the trees, in one tree, training a tree is essentially building out a tree based on thresholds and all of that. Then you now predict. So to predict with a random forest, you simply go through the list of all the trees in your forest, right? And you run prediction on each of the trees. So that's what this is. You run prediction on each of the tree, and you can now use a counter to count the votes. So you get the one with the highest vote, the the category with the highest vote from each of the trees. That becomes your prediction for a random forest. And that's it. It's as simple as that. Um, using so this is using sklearn to do the same thing. And you see how much simpler it is using sklearn. We're using sklearn, you just call it. You're not even thinking about it. You're not even thinking about it's so much easier. But why I took the time to go through this is so that you can at least understand. Look at how easy it is to do random forest. You just, first of all, you import a random forest regressor from sklearn.ensemble, right? Then you fetch your data, right? And then you can do your test training split if you want. And then you just run this. You specify the number of estimators you want to use. In this case, 300. You estimate you specify the approach you want to use to select the maximum number of features to be used for training each tree in your forest, right? And then this is random initialization. And then you run fit on the data. That's it. And then you can now predict. That's how straightforward it is. So that brings us to the end of today's class. We have looked over a lot of different methods and we have gone into detail into the decision trees and random forest. When we resume next week, we are going to continue. We will still look in detail at the other classical machine learning algorithms. So we are going to look at the support vector machine. We'll look at support vector machines. Then we'll look at we'll have an understanding of hyperplanes and what all of this means, kernels and so on. And then after that, we'll look at the remaining ones as well. So then we will do a task where we will use these different algorithms to solve different problems. So that's all from me. Are there any questions? Yes, go ahead. Blessing.
Okay, please. I want to ask, what does the end job? I saw something like end job and random states when you're going through the random forest and scikit-learn. So what do they do? What do they control?
Okay, let me see. Um, okay, that's a number of jobs. So number of jobs is um a way to parallelize the work. So remember, you are training the different decision trees in parallel. So you can actually this is more of a computational optimization thing. So you could actually say, okay, I want to make number of workers that will train in parallel. Okay. But the number of workers that you can train depends on the capability of your CPU, right? So if you pick number of workers that are too much for your CPU, it can drag your CPU. But if your CPU is capable or GPU is capable, um, and you don't use use only one, of them, then you just have slow this thing for no good reason, right? So sometimes it is difficult to figure out, okay, what was the number of jobs, um, or what's the number of CPUs or GPUs I should use, to do this. So -1 now means let the algorithm decide. It will have a way of checking maybe the number of cores in your CPU and all of that, right? Okay. So if you specify none, it's going to use only one core. If you specify a positive integer, it will use the number of cores that you have specified. If you specify -1, like in this case, it will use all available processors on your machine. So it's going to actually kind of check free processor cores, right? Then there's a -2 also, which means it can use all the processors and leave one behind in case you want to do other things. So that's what n job means. The random state is just a random number for any randomization that is done. For example, the initial if you want to initialize anything to random numbers, right? So this is used to seed the random number generator. Okay. Any other question? All right. All right. We are going to um so I know